We're continuing with section 14.7, the extreme value theorem. So the extreme value theorem in calculus 1 was that every continuous function on a closed interval, closed and bounded interval, attains its maximum and its minimum, absolute max and absolute minimum value. Here, extreme value theorem goes if z is equal to f of x and y is continuous on a closed and bounded set D in R2, then f of x and y attains an absolute maximum and absolute minimum. So over there, the analogous to this extreme value theorem in calculus of one variable will give us the closed bounded interval method. Here, obviously, it gives you closed and bounded set in R2 method, basically. What does closed mean? That D contains all the points on its boundary. Bounded means that D does not go off to infinity in some direction. So look at the shape on the left. You can see that all the points in the boundary is included. There's no dashed. The one on the right, there are points in the boundary that is not included. Now, the one in the left and the one in the right are both closed. The one in the middle, the one in the left is closed. The one on the right is not, but they're both bounded. But the one in the middle is unbounded set. As you can see, one side goes to infinity. So basically, the one on the left is the one that satisfies extreme value theorem if you have a function that is continuous over this domain. Other thing to notice is that basically in calculus of one variable, the closed and bounded interval was just an interval. Here, the boundary is more than just 2 points, and it's and there's the interior points. There are interior points that you have to check too. So in calculus of one variable, we checked the critical points and the two endpoints of the interval. Here you check critical points of the function and all the points on the boundary. So there are infinitely many points on the boundary. So what is the closed and bounded domain method? Extreme value theorem, we just repeated, it has to be on extreme closed and bounded domain in R2, and function has to be continuous, then you attain the absolute min and max. So the closed and bounded domain method to find the absolute extrema has to start with critical points, right? So find out the critical points, find the extremum of f on the boundary of D, extrema of f on the boundary of D. So this one requires a little bit of a calculus 1 to it. So you parameterize according to the boundary, you find where f is max or min on the boundary, and then you compare the largest between of 1 and or 2 is the absolute max, and the smallest and the 1 and 2 are absolute min. So the second derivative test is not required here. However, step 2 can be very complicated, and that's why in specific cases we're going to introduce to you another method in 14.8. Example 2. Find the absolute extrema of f of x and y equal to x squared minus 4xy plus y squared on the domain D equal to all x and y such that x squared plus y squared is less than or equal to 1. So the first step here should be to find the critical points. Gradient of f equal to derivative with respect to x, and then derivative with respect to y. Set it equal to 0 vector, and so it's 2x minus 4y equal to 0, and negative 4x plus 2y equal to 0, and this gives you 0 and 0. So you found that, and that's a critical point. Now what I need to do is to figure out the domain. And so domain says x squared plus y squared less than or equal to 1. What shape is that? That's the circle like that, and with the radius 1, and everything inside of it. See, the entire boundary is included. See, equal sign gives you included. Now, I have to figure out what's the maximum or minimum value of the function on the boundary itself. How do I do that? Boundary is this circle. Let's parameterize it. That's a pre-calculus story. This would be x equal to cosine of t, y equal to sine of t. Then plug in the parameterization. So instead of x and y, you write f of cosine of t and sine of t, which is cosine squared t minus 4 cosine of t sine of t plus sine squared t. That is 1, because this and this, according to Pythagorean identity, is going to be 1 minus cosine of t sine of t. Either use the identity of 2 sine of t cosine of t equal to sine of 2t, or just take the derivative and figure out where f is, this f of cosine of t and sine of t is maximum, when is it minimal. So let's call this g of t, because we parameterize it. Now find g prime of t. That is negative 2, derivative of sine is negative cosine, so plus sine of t, sine of t, the product rule, and then negative 2 cosine of t, cosine of t, and that is 4 times sine squared t minus cosine squared t. The easiest way is to actually use the identity here, or you can set this equal to 0, but it would be negative cosine 2t here, and setting it equal to 0 and solving without the identity gives you the same thing if you set it equal to 0 after using the identity. So I'm setting it equal to 0 now, and so negative, so cosine of 2t equal to 0 means 2t is equal to, where is cosine equal to 0? At pi half plus pi. So and so we can write it as k pi now, and so t is going to be pi fourth plus k pi half. Now the circle is, you have basically parameterization of circle like that, put t between 0 and 2 pi. So find all the values of t between 0 and 2 pi. T equal to pi fourth, add pi half, add 3 pi fourth, add another pi half, 5 pi fourth, add another pi half, 7 pi fourth. So there are basically 4 critical points for the boundary. What was the G? G of t was the parameterization of the boundary. There are 4 critical points for the boundary. And so you have to check all these critical points for the boundary. First of all, you have to figure out what those critical points are, and then check them for the boundary. And so what was the parameterization? Parameterization was x equal to cosine of t and y equal to sine of t. So let's set this up now. Point f of x and y, and then we do even more. So if I plug in t equal to pi fourth in cosine of t and sine of t, I get the point is going to be square root of 2 over 2 and square root of 2 over 2. If I plug it 3 pi fourth, and then I get negative square root of 2 over 2 and square root of 2 over 2. Then the other one is going to be both of them negative. And then the last one is y is negative. And there is one more, that would be the critical point of the function inside. Now, plug in all these points inside the function and see which one's biggest, which one's smallest. So the part of finding the first 4 points in this list is the part that takes a lot more time. And we have a method. We're going to show this again in the next section. And you see that there is another method of solving that. So basically, these are the values that we have, and we want to find the f value, and we want to find the classification. It turns out the values of f at the first one is -1, the second part the second point is 3, and then 3 and -1 and 0. So what is the classification? Classification is absolute minimum at 2 points and absolute maximum at 2 points, and then the critical point of the entire function is not any extremum point. So it's interesting to look at the shape of this. See, if you look from above, z-axis is basically pointing like an arrow into my face. I can see a circle here. And so I'll move it around now. And you see that on that circle, which is the domain, it's x squared, I'm sorry, you see a disk, not a circle. And on the disk, you see that that's the domain. And then you see that on the boundary, there are 4 points. 2 of them are local, they're absolute max, and 2 of them are absolute min. And so that's the shape of the function. And so let's do the ICLCA question 14.7c. Let f of x and y be a continuous function on a domain D in R2. Which of the following statement is true? If D equal to x and y, such that x is between 0 and 1 and y is between 0 and 1, then f might or might not have a local maximum value on D. B, if D, again, set of all x and y such that x is bigger than 0, y is bigger than 0, then f definitely does not have a maximum value on D. And C, if D is closed and bounded, then f definitely has a maximum value on D. If D is neither closed or nor bounded, then f definitely does not have a maximum value on D. So according to the extremum value theorem, if D is closed and bounded and function is continuous, then we definitely have a maximum and minimum on the domain. Okay. Now, Euclidean 14.7d. Suppose that P of A and B is a critical point of a function f of x and y. Which of the following guarantees that P is a saddle point? A, fxx and fyy have the same sign at P. B, fxx and fyy have opposite signs at P. C, fxy is negative at P. D, fxy is positive at P. So take a break and come back and then solve the question. Now, let's discuss this. We've done a little bit. If the discriminant is positive, f of xx and f of yy have to have the same sign. And so if if fxx, but now what if fxx and fyy have the same sign? Does it mean that discriminant is positive? No, but fxx and fyy having an opposite sign, it actually it ensures that the discriminant is going to be a negative sign, because look at this, it's just basically fxx fyy minus fxy to the power 2. This part is going to be negative. If I ensure that this part is negative as well, then the entire thing is going to be negative. And so C and D don't work because knowing whatever fxy is does not change the sign of whatever the sign of fxy is, does not change the sign for the discriminant.